Welcome to our talk. My name is Lynn Root. I am a senior or staff engineer at Spotify. I've been at Spotify for 6 years, working in infrastructure for 4. I'm also the internal sort of free and open source software evangelist. Yeah.
Hi, I'm Fallon. I'm a senior software engineer at Spotify. I've been there about 4 years. I work on the same team as Lynn, and we've been focused on infrastructure for audio processing for the last year. And today's talk is about the design and architecture of a suite of libraries that we've built to support audio intelligence research. So to start with, what exactly is audio intelligence research? This is the sort of fancy phrasing from our research website. But basically, it's anything that advances the state of the art in understanding music at scale to enhance how it is created, identified, and consumed. More concretely, it would be stuff like finding the beats, the position of beats in a song, and finding the tempo of a song, finding pitch, doing cover song detection, and all of those things can be put together to become building blocks for features in the app. Our research team also contributes back to the community by publishing data sets and papers to describe their work. And but as infrastructure engineers, the thing that we really care about is the at-scale part of this description. We really want the researchers to spend all their time thinking about their research and not worrying about managing deployment or writing libraries for distributing work across multiple machines. So, of course, like in order to understand how to build tooling for them, we had to think a bit about their research workflow and capture it. And to start with, so audio researchers typically start with a single audio file or some audio metadata. They apply some transformation to it and get some useful information out. So again, like for example, you could find the positions of the beats in the song and the tempo. As you might imagine, research tends to build on other research. So once you have the beats and tempos of 2 songs, you could write another transformation that finds the optimal way to mix them together. And so then you can say, okay, I can chain multiple transformations together with one depending on the output of the other. And pretty soon you say, okay, this looks a lot like a directed acyclic graph. And this happens to capture pretty well how researchers work. And finally, once researchers are done developing their algorithms and this graph of transformations, they typically want to run it across the entire catalog of songs. So for example, if you wanted to make it possible to mix any 2 songs together seamlessly, you would want to find the beats and tempos for all songs. Okay, so now that we've described how researchers work, we kind of need more specific requirements for productionization. So we just talked a bit about graph execution, or the fact that the researcher's work can be described as a graph. We want to talk also about what types of execution they need across the graph. And it turns out that there's 2 forms, top-down and bottom-up execution. So with top-down, every transformation in the graph is run for every audio file submitted to it. Let's say we have a graph of transformations. A reference to an audio file is submitted somewhere in the graph. The transformation is run. It submits work to its child nodes. Those run. Those submit work to their child nodes, and so on until every node in the graph has been executed. And that's top-down processing. The other mode is bottom-up. It's not always efficient or necessary to run every transformation in the graph. A lot of times you just want to run one, which means you may need to run its parent transformations to fill in any missing dependencies. So, for example, we have our graph of transformations. Submit work somewhere in the graph. Let's say it runs and notices that its upstream dependencies are missing, so it resubmits work to its parent. Let's say those are missing as well. Resubmits work to its parent. Let's say all the dependencies are there, so this transformation runs. Once it's done running, it submits work to the child that called it. And you'll notice that it only submits work to the child that called it and not all of its children. And then once that's done, it resubmits work to the original node that called for this transformation. And that's just basically bottom-up processing. It's useful whenever work needs to be run in just one branch of the graph. Okay, so we've talked about how work gets done within the graph of transformations, and now it's kind of important to talk about what goes into the transformations themselves. So first of all, pretty much all of the code that gets run is written in Python. It's a really popular language with audio researchers. Most of them aren't trained as software engineers, and they learn Python at some point in school. The most dependent upon audio processing libraries are in Python, and the most recent research makes a lot of use of machine learning, which is another area in which Python predominates. So we need a solution that allows us to use Python. Researchers also need reproducible control over their environment. They need to be able to install any dependencies and bindings they need. We've also noticed that the workload looks much more like a streaming workload. Audio data needs to be processed as soon as it arrives, rather than waiting for a specific time window to close. Like for example, when a new song is released, we want to extract features from it immediately so that the track can be included in our algorithmic playlists. Researchers also want to avoid duplicate work. Most transformations are pretty expensive to run, and you really only need to run them once if the code doesn't change and the data doesn't change. So the system needs to make sure it does existence checks on the output of these transformations. And finally, once again, the system that we build needs to be scalable across the entire catalog of songs, and this runs in the tens of millions. So yeah, just to summarize the requirements, it needs to support top-down and bottom-up processing. It should support Python. Should support and allow for researchers to customize their environment. There should be some way to avoid duplicate work. It should support a streaming workload, and it should be scalable. So what did researchers do before there was an infrastructure team? We can look at their early approaches. They started with something they called the music intelligence pipeline. What this was a graph of Dockerized service microservices that listened to pub/sub queues for work. Each service handled a single transformation with an input topic to receive work and an output topic to signal the downstream jobs that work was done. This met the basic requirements. You could run Python inside the containers. You could install whatever you want inside the containers. This obviously manages a streaming workload. It makes it possible for you to implement an existence check. And if you want to scale this, you could with a lot of effort. Around the same time this was being developed, Spotify was migrating our on-premise servers to Google Cloud Platform. Apache Beam running on Google Cloud Platform Dataflow became very popular within the company for batch and streaming processing workloads. So just for a side note, for those of you who aren't familiar with Beam and Dataflow, Apache Beam is a language agnostic programming framework that unifies both streaming and batch workloads, and Dataflow is one of the runners. So Apache Beam provides a Python SDK, and Beam also added an experimental option that allows users to define the Docker containers that run on workers. And what this amounted to was that the researchers could replace the microservices in their previous solution with Apache Beam jobs running on Dataflow. Since Dataflow is a managed service, it's made their lives quite a bit easier, in the sense that it's much easier to deploy the code and scale it. But there's still a bit missing. A graph of streaming Dataflow jobs is still really complicated and error-prone to maintain. On any single job, there are a lot of steps to take when code changes or data changes, or if you want to change any aspect of the job's configuration. If you want to change the worker type or the number of workers, you have to shut down your job and change the configuration and start it back up again. This really wasn't that great for a research workflow. And there wasn't any built-in support for top-down or bottom-up processing. And we also found that off-the-shelf orchestration systems such as Luigi and Airflow weren't a great fit for this use case because they aren't really focused on streaming jobs. So.
All right, yeah, to address all these missing pieces, we formed a team to formally support this workflow. And we ended up developing a tool called Klio. So at Spotify, we have a tendency to name our software after Greek mythology. And so Klio comes from the Greek muse Clio, with an E, and she was the muse of history and lyre playing. However, we dropped the E to avoid any confusion, which also made it a nice complement to our other Apache Beam tool in Scala called klio. And so klio is meant to provide a user-friendly layer of abstraction for executing and managing a DAG of transforms. It's also an opinionated approach on streaming Beam jobs in Python on Dataflow, and it's particularly tuned for audio processing. It provides a more Pythonic API for writing a Beam job, allowing researchers to focus on the core of their problem rather than worry about pipeline configuration and execution. It supports both top-down and bottom-up execution of pipelines, and those pipelines might be owned by multiple teams across multiple Google Cloud products or projects. It has ping mode to follow the path of a DAG without triggering any work. And it's also optimized to not redo any work that's already been done, but it allows the user to do so if needed. It makes use of Apache Beam's portability framework, allowing folks to create a Docker image with the exact environment needed, including any non-Python libraries. And then finally, it can be easily deployed via CI/CD with no dropped messages, allowing for a quick iteration. And so klio isn't really a single thing, it's more of an ecosystem. And so from the point of view of the user, they mainly interact with our CLI tool. So users can pip install klio and get to work immediately. Sorry for the small text. This is basically klio create job. It generates the necessary files and creates resources in Google Cloud, and then produces like a hello world-like example of a transform. So then once folks implement the actual logic of their transforms, they can run a klio run job. And so this deploys everything needed to Dataflow and kicks off that job. Or if configured, it can be ran locally. Now that the job is running, you'll probably want some work to be done. So then users can invoke klio publish with the desired audio IDs, and then messages will be published to the job's input queue to kick off work. So then once you're done with the job or need to iterate, a simple klio stop job will do. And so one of our goals when developing klio was to give a very simple API for users to abstract away a lot of the work that is unrelated to their job. And now if we peek under the hood a little bit, we can see that a bit more heavy lifting is being done by klio. So if we look at running a job, users can invoke this on their machine or have deployments triggered by git push, making use of our CI/CD. Either way, behind the scenes, klio will build a Docker image that will be both the worker on Dataflow as well as the driver. And the driver is a part of Beam, the Beam pipeline that actually launches and kicks off everything. So user-defined transforms, configuration, and Python and system requirements are installed in this image. And so once built, klio run job actually runs the container with additional setup required for kicking off the job, like environment variables pointing to user credentials. So within that Docker image, we also install a tool called klio runner. This is a simple tool that actually runs the Beam pipeline job with the user's configuration, and that's the driver part. And then this image gets uploaded to a Google Cloud registry. And then on Dataflow, Dataflow and Beam kind of just take it from there. Dataflow will orchestrate the pulling down of that image, spinning up the needed resources and machines, and running the containers across those resources. And then Beam will distribute the work across those. Google Cloud Storage is actually used for two separate purposes here. The one that is not seen by users is the serializing and pickling of Python code that will be distributed and unpickled onto workers. This is taken care of by Beam and Dataflow. Thankfully, klio doesn't have to touch this. The purpose of GCS that users do see and what Clio leverages is data input and output. And so Clio also makes use of stack driver monitoring for any metrics that the users are interested in, which can be push to PagerDuty if needed. Data flow logs everything to stack driver, and then Clio also generates log messages that are captured there, and then users can use a part of the CLI tool to look up those logs. When generating work, Clio Publish will publish Clio messages to the job's configured input topic on a Google PubSub. And so all of this heavy lifting is done that the user doesn't see, that the user doesn't really see. And this is actually only two parts of the Clio ecosystem, the CLI and that runner. There's a third part of the ecosystem called the Clio library, and actually kind of defines a bit of architecture. So if we zoom in a bit to see what a kliojob actually is, it's the user's transform code plus configuration plus the Clio library, and then which I'll get more into in a bit. So the kliojob consumes a message from PubSub, and then there's some like pre-processing work being done. It unpacks the consumed message and decides how it should be handled. Should this job actually do work for this audio ID? Does the input data that's required actually exist, et cetera? And I'll dive deeper into that in a second. But after pre-processing, if all is good, it then passes off to the user's transform. So within the user's transform, they can then securely download the input audio from GCS through another helper library, and then upload the results to another bucket in GCS. Once the user's transform is done, there's some post-processing. There isn't much, just handling if the user errored out, and reserializing data as a Clio message, and then that is published to the job's output topic. So going back to the handling of the message in pre-processing, when the team behind Clio first organized, we didn't know if we would be a permanent team or not, and that sort of influenced our design decisions. We shouldn't be building any services that we won't be able to maintain. So being stateless was key. And that's evident in the contents of the Clio message that gets passed through PubSub. So a Clio message is considered a unit of work that a transform needs to handle. It contains a unique ID that refers to an audio file, or perhaps even a list of IDs. And this data is the data that the user's transform will actually work with. The Clio message also has metadata attached to it that the user doesn't really see. And this metadata influences how Clio should handle the unit of work, which is best shown in a little flow chart. So after Clio consumes a message, it essentially first handles if this is bottom-up or top-down execution. It's basically if the Clio job is in the downstream path of the message, and if not, then it's a bottom-up execution flow, and it's not meant to handle this piece of work. And so Clio just drops the message and stops handling it altogether. However, if the job is in the downstream path, or if there's actually no downstream path at all signaling top-down execution, then Clio moves on to the next check, which is this message in ping mode? And so ping mode follows a graph obeying top-down or bottom-up execution, but not triggering any work. So if it's in ping mode, then the message is just passed through and published to the job's output topic. If not, then Clio proceeds to the next check. Does output data for this unit of work actually exist? We want to avoid spending time and resources on work already being done. So if the output data does exist, then the next check happens. Should we actually force work to be done again? Maybe another version of the transform is being used, so we actually do want to redo all the past work. If not, then the message is not worked on and published to the job's output topic. If it is in force mode, or if the data doesn't actually exist, then Clio continues on to the next check. Does input data actually exist? If it doesn't, then Clio will add itself to the list of downstream jobs in the message metadata, and then it's published to the parent's input topic. Clio then drops the current message, since there's no need to hang on to it, as it will get a new message once the parent job is done and the input data exists. And then if the input data does exist, then we're good to go to process. Clio will invoke the user's transform to apply that to be applied to that unit of work. So I know the design and architecture of Clio is super interesting, and maybe you're all thinking you want to see some code, maybe. So we'll demonstrate, we'll make use of an automixer algorithm, which takes 2 tracks of different tempos and then blends them together to make them feel seamless, much like a DJ does. And so we have 2 input tracks and a single output track. The transform itself will find the beats and the tempo of each track and then find the optimal tempo for matching between those 2 tracks. The transform will then find the crossfade region, and in that crossfade region of both tracks, we'll either speed it up or slow them down appropriately so that they match. And then finally, we'll concatenate those 2 songs to make one file. And so I'll first show this job, or how this job would look like in a vanilla Beam without Clio. And comparing these 2 will hopefully show where Clio shines best. So we might have the following files. We have a job requirements.txt to define the job's Python dependencies. One might also have a Docker file to have a repeatable and clean environment, or make use of Beam's portability framework. Mixer.py and trackstorage.py contain the actual transform logic and helper tools. And then run.py sets up the pipeline for execution. And so if we take a look at run.py, it's actually a lot. You're not meant to be able to read this code. It's about 125 lines of code. And again, this is not actual mixer code. It's all just boilerplate related to configuration, related to downloading and uploading data, and checking if input and output data already exists. Now, if this is running on Dataflow, you'd first build and upload your worker image, and then run run.py to kick off the job. However, Python dependencies on a developer machine can get quite messy. Running a pipeline this way can be problematic because your local development environment can be different than what's on the worker image. And so a solution to that is actually executing the pipeline within the worker image itself, like so, where you would run your image with the appropriate flags and mounts environment variables, but it can be easier. And so now we're going to Cliofy all of that. So there's not much different in terms of the anatomy of the job when looking at the directory of this directory structure. We do have a new file, one that contains pipeline configuration. And then if we look at run.py, we can see that it is a lot smaller, only 50 lines of code, where Clio essentially abstracts away boilerplate code and configuration for the user. And then, well, it's a lot simpler to run as well. There's no need to worry about differing Python environments or remembering all those Docker flags. Taking a closer look at a kliojob, the user must inherit from our base do fun. This gives them access to their own job configuration, logging, and metrics. The base do fun also wraps the process method that Beam requires to be implemented. And then we essentially intercept incoming work, so pre-processing and post-processing can happen. The user still has to define methods like how to determine if the job has its input requirements or if the work has already been done. And I guess we could even potentially abstract this away, but existence checks tend to not be that clean cut. So overall, Clio strives to simplify defining Beam pipelines for users. So by removing configuration from code to a separate YAML file, it allows jobs to be both portable and quickly iterated on. There's no need to rebuild and publish the entire Docker image when wanting to use higher CPU machines. Folks do not need to worry about differing environments when launching a job, or remembering to include their deployment credentials in the Docker container at runtime, but not actually in the image itself. And so Clio takes care of a user's DAG so that the user can just worry about their transform logic.
All right, so that's Clio and its architecture, and you probably want to know a bit about the takeaways and experiences we've had actually deploying this. So first of all, what worked? The stateless architecture that we'd originally put together to deal with the fact that we might not be a permanent team actually worked out really well. What it ultimately worked out to was that maintainers ended up being decoupled from the users. We've been able to iterate very quickly and add new features without creating breaking changes. Also, despite the fact that this was developed for a research workflow, product-focused teams wanted to use Clio because it made working with streaming data flow jobs so much easier. Right now, we're seeing like 3 teams internally using Clio with multi-node DAGs, so it's not just a simple transform. They're actually making use of the bottom-up, top-down processing, and they're scaling it to tens of thousands of messages per day. We've also just found it's been really productive, kind of opening up our code base to our internal customers and just working with them as closely as possible. A lot of times, if they have an issue, they'll open a PR and we'll review it and put in a feature. You might also wonder what was hard. From a technical perspective, we were surprised to find that not that much. We were working with experimental and not quite GA features, but for the most part they worked, or Google helped us out. The biggest headaches tended to be dealing with serialization and deserialization errors and dependency conflicts. Finally, what's next? We're actually working on open sourcing Clio, so sometime next year you can actually go check out the code for yourself and try it out. Internally, we're planning on adding features to make it easier to scale Clio graphs to larger workloads. At the moment, it's still a pretty hand-tuned process. There's a whole list of features internally that we're building out. We want to improve Jupyter Notebook support, and we want to put some thought into trickier design questions like, what does it mean to have batch processing within a Clio DAG, and how do we manage multiple inputs? And yeah, that's all. Thanks for listening. We're hiring. Come work with us. And if you have any questions, come talk to us at the coffee breaks.